Hello students, welcome back. We are done with two sample inference of two dependent samples. Now let's consider two independent samples. We can consider proportions and the mean. Proportions first because that's a little bit easier. We don't have to deal with the t-curve. It's just going to be just z-curve with central limit theorem. Of course, we have to assume large sample size. Basically, what you do is to take the difference between the observed proportion and take appropriate standard error, which happens to follow the Pythagorean rule. And why Pythagorean rule? The real detail is actually covered in chapter 5 of our textbook, but that requires multivariable calculus, so I skipped. So if I give you some visual help, it's kind of like this. If you have some situation like this, where standard error is pointing toward same direction, kind of like this, so pulling this way actually contributes toward this way as well. So they are not independent. If you pull this way, then the contribution horizontally is going to be negative the other way around. So we don't have independence there. So independence can be visualized geometrically like this, and that corresponds to Pythagorean theorem. And you can deduce all these rigorously using multivariable calculus. So in the end, we have Pythagorean, and after everything is said and done, we end up with this SE formula. As a matter of fact, we can deduce it from Pythagorean rule like this. Standard error for the two sample inference for two independent samples can be written as Pythagorean rule, square root of SE1 squared plus SE2 squared. But SE1, we follow this SE formula for proportion, square root of P1 minus P over N for sample 1. So P1, 1 minus P1 over N1. And then we square the square root, so that's gone. We end up with this. Do the same thing with the second sample, P2, 1 minus P2 over N2, like this. And that's how we end up with this formula here. All right, so much for theory. And let's talk about how to utilize this. Please remember this SE formula. All right. Here's an example problem, and please stop the playback and read through first. So, in studying his campaign plans, Mr. Morris wishes to estimate the difference between men's and women's views regarding his appeal as a candidate. A sample of 1,000 voters were taken from each population, so 1,000 men and 1,000 women, and 388 of 1,000 men selected, and 459 of 1,000 women selected favor Mr. Morris. So basically, for men, is 388 over 1,000, so that's 0.388. For women, 459 over 1,000, which is 0.459. Okay, and we want to find out the confidence interval for the difference. What is the best point estimate? And this is, let me cheat, I cannot do this with mental maths with just talking and writing at the same time. So here we go. So that is the observed difference. Nothing is accurate in statistics, so let me use approximation symbol everywhere. And this is proportion of the difference. So if you want to be really precise, you can use proportion for the difference. So, let's use D for difference. But, oh, come on, I'm not going to bother this. I'll simply use P. And then I can expect a normal curve around this P. So let's see. So we have this kind of picture. So 7.1% point difference. And then we're going to find out what, 99% confidence interval? Okay, all right. So 99% in the middle like this. And then the other 1% should go either here or there. And then same goes here. It's really difficult to draw these numbers with mouse. I'm not writing, I'm drawing. That's why everything is lousy here. And then, of course, we can use the usual technique to find out the endpoints of these intervals. Let's say this is left-hand side and that's right-hand side endpoint. End minus center over SE. So, for example, if I want left, L minus center over SE. And this is the z-score you have to look up from your normal table. Associated is to 0.005. If I remember correctly, that z-score is 2.58 or 2.575, something like that. I erased the picture a little bit prematurely, but that's okay. I'm going to show you the real picture real soon. So it's kind of like this. So n minus center over SE is your z-score. So basically you end up with this. Z-score is n, so whatever, x value. Left-hand side or right-hand side? Okay, left-hand side. And then center over SE. And this z-score will be 0.0575, yeah, this one. Look up the z-table. And this is left-hand side, so it should be negative. And z-score for the right-hand side endpoint is gonna be, by symmetry, is gonna be positive. And thus we can solve for L and solve for R, you're gonna get that. L is approximately equal to 0.071 minus the z-score of 2.575 times the SE value. And the right-hand side, by symmetry, I can change this into plus. And once you know the SC value, plug those in and do your computation, you're going to get the confidence interval. The same idea as before, same normal curve analysis, same z-table. Now what is SC? That was the real kicker, wasn't it? And that formula was P1, 1 minus P1 over N1 plus the same thing here for the second sample, P2. Nothing is accurate in statistics, so it should be Wrigley equality all the time. Oops, wrong key. And this one was, I forgot, 0.38. 388 men, 459 women. So 0.388. And sample size of 1,000. Zero 0.456459 and 0.459 and then 1,000. And this computation will yield the SC value. It'll turn out like this if you do it right. So far, everything is just computation, isn't it? So this is your SC computation. And that number, which I just highlighted in red, will go right here. Finish your computation, you're going to get the left-hand side and right-hand side endpoint of the confidence interval. If you do it right, you're going to get 0.014 something, so about 1.4% point difference, versus 0.127, like 12.8% point difference, approximately speaking. That is 99% confidence interval. Now, for this problem, for computational simplicity, we used just 1,000 people so that the proportion was easily calculated by mental math. These computations require a calculator, but many of those computations were pretty simple. But I could have tweaked those. I could have kept same 388 men out of 1,000, say 69 men, and 459 out of 996 women. Okay, that will change things a little bit, right? So, so the proportion will change accordingly. So, let's see, proportion. Those are approximately explicitly there. Let me change things just a little bit. I changed it to 10,069 men and 996 for women. Okay. So for women, no, for M1 is women in this case. Okay, I have to change that. So this is 459. And this is 388. And then P1 is M1 over M2. P2 is M2 over M2. And I wonder what those values are. So let me uncode those. And then this one, okay. All right, there you go. Ooh, okay, all right. For women, 42.9%. For men, 36.3%. And then SE is 0.215 something. And then the picture changes accordingly. Okay. The observed difference was 6.64 percent point difference, and then changed a little bit. You see, all these things work even if we have two different sample sizes. These numbers, all these numbers will have to change accordingly, but that's about it. So don't be fooled by the simplicity of the example problem set where we had the same number of men and women to begin with. It was just for simplicity. We don't really need that kind of simplicity. We could do much better in much more general setting. Okay, so much for interval estimation, and we're going to talk about hypothesis testing example in a separate video. Stay tuned, coming back soon.